problema. Tuanan, ele parou e separou aí um tempo de 1h30 para a gente estar junto, né? Então, a ideia é que a gente possa extrair aí o máximo do que ele tem aprendido ao longo desses anos, aplicado, né, nos trabalhos. Vai ser uma lecture assim, muito importante e especial. Muito especial ter o Tuanan aqui com a gente, né? O Tuanan, para quem não sabe, ele foi o primeiro doutor formado no grupo MolMod-CS, tá? É um prazer tê-lo aqui conosco nessa tarde. Então, agora vou fazer a apresentação em inglês. Mohamed e Nafia are here with us. This is a lecture, okay, that will be given by the researcher, the Dr. Tuanan Lourenço, okay, from theory to simulation, calculating transport properties in electrolytes through molecular dynamics. Tuanan, it's a great pleasure to have you here with us. The word is with you. Thank you.
Just coming back. So as I said, I work in Tuanan and Cine inside the computational material design.
Tuanan, just to be recorded, okay, in our presentation, could you just go a little bit back and present? This group. Okay. Yeah, can you present?
Yeah. So today I'm a postdoc researcher and project leader inside the Tuanan group. Tuanan group is a research group in the University of São Paulo, Institute of Chemistry of São Carlos. Is the group of Professor Juarez Lopes Ferreira da Silva. We are located in São Carlos. In the Tuanan group, we have different areas and topics. So we have people working with multiphysics, DFT of molecules, DFT for solid state, and also machine learning and molecular dynamics. Tuanan is part of Cine, the Center for Innovation on New Energies. That is a virtual research center sponsored by FAPESP and Shell. In Cine, we have 4 main divisions: the energy generation, advanced energy storage, green hydrogen, that are the 3 experimental divisions. And we have the computational materials design, that is the theoretical division, that is the division that I'm working. Since Cine is a virtual research center, we are spread out in different universities in São Paulo State. And inside the CMD division, we have different projects. Those projects are some kind of mimetization of the experimental divisions. So we have people working with photovoltaic applications, green hydrogen productions. We have the project for materials for supercapacitors and ion batteries. That is the project that I am leader. We also have another project working with batteries and supercapacitors, but in this case using a multiphysics approach. And we have 2 projects working with artificial intelligence and machine learning. So this is just a brief introduction about what I'm doing in my life now after I left the MolMod and got my PhD. And since I have worked with batteries and supercapacitors, of course, in my PhD, I also worked with electrolytes. So I have learned a lot along these years about how to compute transport properties, especially thinking in batteries applications. So I will just try to introduce a little bit why it's important to investigate transport properties, more specific diffusion and ion conductivity, giving as example a battery device. So if we think, let's just try to be the simplest possible. In a battery, we have the anode, the negative electrode, the cathode, the positive electrode. And when we discharge the battery, in this case, let's think about a sodium-ion battery. This sodium ion leaves the anode, go through the electrolyte, and reach the cathode. This is how we transport charge inside the battery. When we recharge the battery, the sodium ion leaves the cathode, go through the electrolyte, and reach the anode. So we are talking about the transport of the charge and the mass inside the electrolyte. So that means that we need to understand how to control those properties in such a way that we can try to improve the performance of the battery or even the safety of the battery. Because sounds like that we are just talking about performance, like how fast or how slow the sodium is moving. But the diffusion here also is going to dictate how the interfaces are going to be formed in the cathode and also in the anode. So controlling the transport of charge and mass inside the electrolyte, we can control the health, the cycle life of the battery, and also the performance, the amount of charge that we can transport, storage, and how fast we can recharge or discharge the battery. In a simple way, we can say that we have two types of transport properties. We have mass transport and we have charge transport. In the case of the mass transport, probably you can remember from your physical chemistry class, we have diffusion, so in this case, diffusivity. And in the case of the charge transport, we have ionic conductivity. So let's think about the diffusion. So what is diffusion? In a very simple way, diffusion is when we have one particle going from one place to other. A liquid electrolyte, everything is moving inside the electrolyte. So remember that all the atoms and molecules are always rotating, translating. So we have molecules or ions going from one place, one point in the space to the another point. And this is what we are measuring with the diffusion coefficients. We are measuring how fast or how slow one particle can go from one place to the other place. In MD simulations, we can do this calculation using Einstein method or also Green-Kugel. In the next slides, I will talk about it. But just a small explanation about what kind of diffusions we have inside the electrolyte or any material. We have the self-diffusion. So as the name said, is the diffusion of a lonely species inside the space. When I say a lonely species, I'm not saying that this species is a lonely in the space, like we have the electrolyte, we have a lot of water, we have a lot of salts there. We can see the diffusion of a lonely water molecule, but this water molecule is still interacting with the molecules around itself. And also we have the mutual diffusion. So in the self-diffusion, we are observing the diffusion of one particle. If we look here to the equation, maybe this can be a little bit easier to understand. So if we look here, what we are doing the difference between the time, the origin time, and the position in the origin, and also the position in a specific time. So we are just measuring how far the species can go. And again, we are looking to only one species, like we are only looking to J or I here. But we also have mutual diffusion. What is mutual diffusion? In mutual diffusion, we are measuring how far or how fast two particles can go together inside the system. So if you look here, you can see that both equations are very similar, but here we have the square of the delta R of one particle, and here we have the delta R of one particle, so in this case K, and the delta R of another particle, in this case L. So we are measuring how these two molecules here walk together inside the system. In the case of the electrolyte, in general, we do not measure mutual diffusion, but for people that work with like lubricants, they measure this a lot. So this is very important in this field, but in electrolytes is not too much. But we are looking here, so let's think that this is cation and this is anion. So here we can see how fast cation and anion moves together. But since we are looking to mutual diffusion, is the diffusion of all particles together with all particles. So we also have cation and cation, anion and anion, and also cation and anion. So you can think that in a system, we have the lonely diffusion, the self-diffusion, and we have different types of mutual diffusion. It's okay if someone has a question, just stop me and do your question.
Yeah, it's pretty nice slide, Tuanan. Very good.
Thank you. So sometimes it's a little bit complicated to understand why we are looking to mass transport in the electrolyte, because I think for at least almost everybody, when we talk about electrolyte batteries, the first thing that we think is conductivity. But here we are looking only for mass transport. Why? Because if we understand how the mass transport happens, we can also understand deeply how the charge transport also happens. Because in a simple, very simple way, ionic conductivity is the ability of a material to carry charge. So that means that we are basically seeing how fast one particle can go together with its charge. So the first step, we need to understand how this mass, this particle, can diffuse or walk around in the electrolyte. Also, as I said, when we have the battery, we have the formation of some interfaces in the surface of the cathode and also the anode. And sometimes this interface has a lot of constituents, like a lot of molecules that are not ions. So in this case, we need to evaluate how fast these molecules, these neutral molecules, can diffuse inside the systems and how they can reach here the surface of the cathode and the anode. Try to keep
Tuanan, Tuanan, yeah, go to this one, the slide that you show the self-diffusion coefficient and also the mutual diffusion. Yeah, nice, good. Yeah, one thing that I guess could be important for the students here in the class, and I would have your comment about that, because in a practical way, okay, in molecular simulation, yeah, the self-diffusion in general can overestimate it, okay, the ionic conductivity. Yes, and then because the ions in general can move together, but this type of a way to calculate, I believe, okay, you can show later on, the ion conductivity can overestimate the mobility of the ions in the systems. Okay.
Yeah, I think we should always keep in mind that inside the electrolyte or any kind of material, everything's moving. So the particles are always moving, so sometimes together, sometimes lonely. But when we look at the self-diffusion, we are only looking to the lonely movement. So this tends to create this increase in the values, as Luciano said.
Yeah. So then in your lecture, you will show us the way to calculate the ionic conductivity, considering the collective dynamics and also the self-diffusion as well.
Yes.
Yeah, this is the idea. Okay. Okay, nice, good.
So understanding the diffusion, we can improve the understanding about the ionic conductivity, as Luciano said, because those two things are connected. Also, we can understand how other species inside the electrolyte, like the neutral species, also contribute to the battery operation. And also, using diffusion coefficients, we can calculate transport numbers. That is a very important property when we are dealing with electrolytes. So this first part, just to introduce self-diffusion and mutual diffusion. Now, about ionic conductivity. So as Luciano said, we can say that we have two kinds of ionic conductivity. Just one thing, we are talking here about ionic conductivity. So is the transport of charge by the movement of the ions. We are not looking here to transport proton exchange, nothing like this, just the ions moving inside the system. So we have two types, the ideal ionic conductivity and the real ionic conductivity. In the ideal ionic conductivity, what we are doing, we are measuring the self-diffusion coefficient, so this D here, and we are multiplying by the number of particles and the charge of the particle. So that means that we are basically getting the self-diffusion coefficients, so the lonely particle moving, and multiplying this by charge. So this is why we call this ideal ionic conductivity, because we are thinking in a system in which we do not have any kind of correlation between cation and anion, cation and cation, and anion and anion. So when we measure this, the values that we are going to reach are the ideal values or the maximum value that those systems could achieve if we do not have ionic interactions in the system. And this is very useful, but when you look to this value here, to this property, you should be a little bit, you should have a little bit of caution, because you can interpret things a little bit wrong. Also, we have the real ionic conductivity. now we are getting the ionic contributing, taking account the movement of the particles when they are together. So if we look here to this equation, this is basically the same equation that we use here, the mutual diffusion. So we have here delta R for one particle, delta R for another particle. So we are getting the diffusion of the movement of one particle multiplying by the movement of the another particle and multiplying by charge. So that means that here we have the ionic correlation between the particles. It's clear? Some questions?
Yeah, Tuanan, one question. In ideal, when we are finding ideal ionic conductivity, as you say, we find out the diffusion coefficient of that specific ions, maybe negative, positive. Okay, here we see we are using charge on the ions. So that charge will be complete charge or the fraction of charge what we are using in molecular dynamics 0.8 like that.
So this charge will be the charge of the molecule.
Means yes, for what we are finding the diffusion coefficient of, for example, sodium ion, so the charge will be of sodium ion exactly.
Yes.
But it should be it will be plus 0.8 or 1.
Charge that you use in your simulation.
Okay, so he will take my chart from that and find out by what we have seen. Lourenço Einstein means for ionic conductivity ideal system.
Yes, everything here that we use are the informations that we have from the simulation. So V here is the volume of the box, T is the temperature of the simulation. So all the constants that we use here are regarding the simulation. If you introduce a different constant, a different number here, the data that you have is not more the data from your simulation. It's a different data. Because let's think in this way. Even here that you don't have the correlation in the equation, the correlation is inside the data. So when we calculate this diffusion here, we are looking to the movement of the particle only. But this movement is also the result of the interactions within the electrolyte.
Yeah, thank you. But finally, if you give some solid reference, why we use 0.8 chart like that?
Now, this we talk in the next slide. This is a different topic.
Okay. Yeah, sure.
So everybody understood the difference between these two conductivities, and keep in mind that this difference here is just a methodology difference. It's just a concept, because in the real world and also in the simulation, what we have is this kind of behavior here: the interaction between the particles moving together, jumping from different solution shells. So when we are calculating this, it's just a methodology to do the ionic conductivity. Is okay?
Yeah, okay, that's good.
So, as I said, when we have the real ionic conductivity, we are calculating the displacement of the particles in pairs. So we are calculating like cation and cation, cation and anion, anion and anion, and also we are calculating this cation with itself. So when we look to the real ionic conductivity, what we are looking is to the summation of different ionic conductivity in the systems. So here is the total value. This is the value that you are going to compare with the experimental. This is the final value that you have. But also you have the contribution of the self terms. So like the cation, only the cation, like the Lourenço-Einstein, only the anion, the Lourenço-Einstein, and also the cation and cation, anion and anion, and cation and anion. And when we do the summation of everything here, we have the total ionic conductivity. Okay? And if you think, look to this picture here. Here we have the MSD of the dipole. So in the next slides, we talk about it. But we get the ionic conductivity using these curves here. If you look here in black, we have the total. In blue, we have the self of the cation, and in red, the self of the anion. As you can see, here you have a very, let's say, linear behavior. So this means that these particles here can move very fast, easily inside the trajectory. But when we look here to the cross terms, we see that we have a small contribution to this. And when we look to the cross cation, 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 anion, we see that we have a negative behavior. If this is the summation of everything, this explains why we see bigger values here in the ideal when we do not take into account the correlations, because in general, some part of the correlations are negative. So when we consider those correlations, we decrease the value regarding the ideal ionic conductivity. Okay? And one point, using this kind of information here, we can try to understand how the charge is being transported inside the simulation. For example, if we have the negative contribution of cation and cation, means that they are not moving together, they are moving in different directions. If we have cation and anion, positive means that they are moving together. And if we think about like sodium-ion battery, we do not want our sodium moving together with the anion. We want the sodium moving without the anion, because in this way, the sodium is going directly to the cathode and faster than if we have with the anion. So evaluating this parameter here, we can understanding how sodium is moving inside the simulation. So looking to the correlations inside the real ionic conductivity, we can deepen our understanding about the transport of the charge inside the simulation. So just to summarize, when we use the real ionic conductivity, or how we use and when we use the ideal. So first, keep in mind that the ideal is the maximum value that we can have if we do not consider ionic correlations. So in general, we expect that this is going to be the bigger value, biggest, when we compare the two ones. This is really good when you are working with weak correlated system, like salt in water, salt in organic electrolytes, but not too good when you are working with ionic liquids, because everything there is ion. So the ionic interactions play a really big role in the transport of the charge. This is very useful to evaluate trends in our data, because if we look here, the ideal ionic conductivity is the summation of this curve here and this curve. It's really easy to get the values here because we have a very good linear behavior. And also you can see this called as Nash-Einstein or apparent ionic conductivity or NMR ionic conductivity, because in general, the experimental people use NMR to get diffusion coefficients. So they also call this as NMR ionic conductivity. The case of the real ionic conductivity is a little bit complicated to calculate. Let's say that the calculation is a little bit more tricky, so it's more hard. We have a more detailed vision about what's happening inside the system. And also you can see this called as Einstein-Helfand or MSD, collective ionic conductivity. Okay? Now, when we have the two data, the real and the ideal one, what we can do with this? We can calculate the Haven ratio or the inverse Haven ratio. That is the same equation here, but is the inverse. If we are comparing the ionic conductivity without correlations with the conductivity with correlations, we can estimate how strong or how important are these correlations, and we can see if our ions are moving together or dissociated. So when we look to the Haven ratio here, we can see if we have values that are lower than 1, we have like a strong correlation. If we have values close to 1, we can see that we do not have correlations, because if this equation here is result 1, means that the real and the ideal have the same value. So that means that those terms here are not important and only the self terms are important. This is very used in polymer science. So in general, when you look to the electrolytes based in polymers, they measure a lot this Haven ratio, because you can understand how the ions are moving inside the polymers. Here I have the transport numbers. So the transport numbers is one way that we have to measure, that we use to measure how is the contribution of a specific ion to the charge transport. When we look to the ionic conductivity, we are looking to the total charge transport. When we look to the transport number, we are looking how one specific ion is carrying charge in the system. For example, here, this is from the literature, they are evaluating the transport number of sodium. So that means that inside the total ionic conductivity, so these two here, they're looking how much the sodium is contributing to this ionic conductivity. So in this way here, we can understand if we have a good electrolyte, because what we expect of a good electrolyte is not only a high value of the ionic conductivity, but a high contribution of the sodium or lithium to this ionic conductivity. And as in the case of the ionic conductivity, we have the ideal one and the real one. Again, ideal one, we are only looking to the self terms, so we are getting the self term of the sodium and dividing by the ideal ionic conductivity. Or in the case of the real transport number, we are doing the summation of all the terms that have the particle that you want. Like, for example, you want to get the real transport number for sodium. So we are going to look to self-sodium, sodium and sodium, sodium and anion, sodium and the cation, and dividing this by the total one. So with this one here, again, you probably are going to see the same information from here, but here you are having all the description of the system. And again, in general, ideal values will be bigger than the real one. Like here, this is another example from the literature. So this is the ideal one, and this is the real one. So as you can see, both of them are increasing, but you can see here that in the real one, you have negative values. Those negative values here exist because some of these cross terms here are bigger than the self one. However, when they increase the concentration, they probably are going to see more and more contribution of the self term and a higher value for the transport numbers. So looking here, they can understanding how the correlation between the lithium and the anion and cation is decreasing the contribution of the lithium to the total ionic conductivity. Also, we can use this kind of properties here to try to evaluate if we have some changing in the diffusion mechanism inside the simulation. For example, here that we see negative values, and in some points they have positive values. So this abrupt change here in the transport number probably indicates that something is changing in the mass and charge transport inside the system. So something here changed, like for example, the coordination of the ions, the structure of the polymer, something is changing, and this value is having this abrupt change. So it's okay?
Yeah, that's okay.
Yeah, thank you.
Okay, so this was to try to explain the concept and the importance of the property. Now I will try to show how to do this the practical way. So I will try to show some data, how I use the codes, how we can do some best practice, something like that. So if you have questions when I'm showing the data, just stop me and we can talk about it, okay? Up to now, I just showed you how to do the Einstein method to calculate diffusion and ionic conductivity. But we should keep in mind that there are different ways to calculate those properties. In equilibrium MED simulations, we have two main approaches, the green cube approach and the Einstein approach. In the green cube approach, we are using the integral of the autocorrelation function. So for example, if we are calculating diffusion, we have the autocorrelation function of the velocities. If we are calculating ionic conductivity, the autocorrelation function of the velocities multiplied by the charge. But in the case of the Einstein method, we are using position. So we are looking to the mean square displacement of the positions of the particles inside the simulation. Both methods should give you the same result, but when I say the same result taking account the statistics, so do not expect like the same number in both methods, but the trends will be very similar, and also the result itself will be very similar. What is the difference between them? The difference is the theory behind the approach. So in the green cubo, we are sampling in low times. So in green cubo, I will show you some stuff here. Just a second. So this is a recent paper from the literature. So it's a package to calculate transport properties using green cubo and Einstein method. So in green cubo, we are using autocorrelation functions. And the problem of the autocorrelation functions is because we are looking to the sampling in small times. So it's hard to see the convergence of this data. So although we are doing very short simulations, the cost of these methods can increase a lot because you need to run a lot of replicas to try to get an average here to see the convergence of the ACF. Because what we want is do the integral of the ACF and see the plateau here to get the ionic conductivity. However, this is a little bit complicated. So sometimes people say that the green cube approach can be a little bit hard to converge, and this can increase a lot the cost of the simulation. Also, again, since we are looking to small simulation times, so this is like just 1 nanosecond, you need to save your velocities very often. And this increases a lot the size of your trajectory. So sometimes green cube can be impractical because you need very large hard drives. Also, since we are looking to small simulation times, how often you save the velocities can impact a lot your data. So sometimes it's necessary to do some tests to see if you have a good sampling or not. In the case of the Einstein method, we are using only positions, and the difference than in green cube that we are looking to behavior in short times. In Einstein method, as I showed here, we are looking to long time simulations. Like for example, here we have 8 nanoseconds. So that means that here we can save the data less. However, if you are working with grommets, Einstein methods. But if you are using green cube, you need to save velocities, and this is a readable file, so this can increase a lot the size of the files, while the Einstein not. Another positive part of the Einstein, it's easier to converge because we are looking to long time simulations, and also, in general, everything that we do in these simulations, we need long times. So if you are using Einstein, you already have your simulation to do your RDFs, ADFs, SDF, whatever you want. But in green cube, in general, you need to run a long simulation to calculate other properties and very short simulations to get the transport properties. But in the end of the day, it's a matter of choice. In general, I prefer to use the Einstein method because this is how I learned with Luciano in my PhD, and because you can implement this very easier regarding the green cube method. So from this point to now, I will show data regarding the Einstein method for diffusion and ionic conductivity. Also, just to highlight, both methods are implemented in different packages. You can use this in different softwares. So it's really easy to find softwares to use both methods. Before we start, just one important point before you do your calculations. In general, it's better to have NVT simulations to calculate transport properties, because in this way we are perturbing less the system than in the NPT. But there are several papers that show that if you use the correct barostat, the correct setting for the barostat, you can also calculate transport properties in the NPT. And also, you should know how your thermostat works and what the settings you are using inside your thermostat to ensure that you are not perturbating the displacement of the particles inside the NVT or in the NPT. Also, a very important point is it's really good to know about your force field, because sometimes you can have a very good force field for structure that is not good for transport property. So that means that you can do your best, you can do the most fancy simulation way. If your force field is not good to describe the transport property, your data is not going to be good. So before you start your simulation, it's always good to read about the first field, to look for similar simulations to see if your first field is able to reproduce the property that you want. And also about sampling, as I said, if you have Einstein, remember you need long simulations. If you have Green Cube, you need small simulations, and you need to save your properties very often. And to finish this slide, check if you have your trajectories unwrapped or not. Because in general, for transport properties, we need to use unwrapped trajectories. And sometimes some codes only evaluate the property and they do not change your trajectory. So that means that sometimes you calculate everything, and after some time you realize that you used the wrong mode of your trajectory, so everything's wrong. So always pay attention to this. And also there are some recent papers that they show that the method that you use to unwrap the trajectory can also impact the data for the transport property. These checkpoints here, you can find it very easy in, just a second, this paper here. I will send all those papers to Luciano when I finish. Here they give you some checkpoints to see if you have everything to proceed to your calculation. So it's a pretty good paper to read, and it's also very easy to read. Okay, so as I said, we are going to use Einstein method to calculate the self-diffusion coefficients. So what we are doing in practice. So again, we are measuring the displacement of the particle, so delta R. So we are doing the difference between the origin time and the time in time t, t1, t2, and so on. So in the end of the day, when you finish your calculation of the MSD, you have something like this. So here we have the origin time, and here we have the simulation length. So we can see that when we increase the time, we can see that the particle is moving farthest and farthest. And one interesting point when we look to the MSD is that the MSD can describe different behaviors. So we have here a ballistic behavior. So here we have only like rotational dynamics, only thermal vibrations. So the particle here is not moving. Here we have a subdiffusive regime. So we can think here that the particle is starting to moving, and in the end you have the the diffusion of the particle. So that means that when you are calculating the self-diffusion coefficient, you need to use this part of your MSD. And to do that, what we do is the linear fitting. So you calculate the MSD and do your linear fitting here. And keep in mind that in MD simulations, we are always calculating averages. So that means that this is the MSD, the average MSD for all the particles in the system. So if you look to the individual's MSD, you are going to see something like this. Here in black, we have the average, and here in gray, we have the individual MSD of each particle in the systems. So that means that in average, we have this behavior, but we have particles that are faster or slower than the average. And calculating the MSD can be a little bit tricky because you can improve your statistics in the simulation without doing more simulations. So as I said, this is the equation that we use. So we are always doing difference between times. But one thing that we do is changing the time origins in one way that we can try to use one simulation as if we had several simulations. For example, think here in our timeline. So each block here is a time step. Sorry, is a step in the simulation. So this is our trajectory. So when we are calculating this, we are doing the second. We are doing time 0 minus time 1, time 0 minus time 2, and so on. So we do this from here to the end, and we have the MSD of one particle. If we do this in this way for all the particles, the statistics inside the MSD will not be good. We are going to see something like this. Can you see here that we have some kind of spikes here? We don't have a good definition. So it's hard in these bad statistics to find a linear regime. So what we do this approach like 0, 1, 0, 2, and so on, but we also shift our 0 for different positions. So let's say that we do this procedure, then in the next step, we still with the same molecule, but now we consider here as 0. So we are going to do this guy minus this guy, and so on. So this is like, if we here we have one timeline, here we have another timeline. The next step, we shift again the 0, and here we have another timeline. So in the end of the day, we have one trajectory, but we do our calculation in one way that we use different time origins. So it's a statistical trick that we do to simulate if we have several trajectories. But keep in mind that as we approach to the end, we are decreasing the amount of samplings in the MSD. And this is why when you look here in small simulation times, you have a really good definition. But when we look here, you have this spike stuff, because if we do this shifting, always in small times, we are going to have a lot of sampling. But in long times, we do not have too much sampling. And I know that this sounds a little bit too much technical, but in the last days, I have did a lot of tests regarding this, and you can literally improve a lot the quality of your MSD just playing the number of time origins, the shifts that you do inside the simulation. And this creates a lot of confidence in the data that you have for the self-diffusion coefficient. Questions? Okay, so I will go ahead. And also another trick that this is very, very tricky because there is no rule about it. The difference here when you shift the 0 to other places, this depends of the material that you have. For example, if we have water, we have very low viscosity. So that means that if you go from here to here, we know that the system, there is no correlation between these two positions. But when you have like a very viscous material, like a liquid polymer, sometimes you need to shift this to longer distance to ensure that you are sampling different states. Because if we sampling too often, like 0 here, 0 here, and so on, we are sampling always the same information. So that means that although we are doing several calculations, the result will always be the same because everything is the same. In Gromax, you can control this by, let's see a second, these flags here. So with this flag here, you can say the difference in time between your shifting time. So if you increase it here, you are going to decrease the sampling in the simulation. And if you decrease, you are going to improve the sampling. And this is why when we look here, you can see that in black, I used a shift of 12 steps. In blue, 1,200. So you can see that blue is very spike, and 12 is very, like, you have a very good definition. Okay, but also keep in mind that if this is too small, you're also going to have problem here. So when you are calculating the self-diffusion coefficient, try to use like intermediate spaces, because here you ensure that you have a good sampling and you don't have too much noise. So as I said, to have the self-diffusion coefficients, we need to do linear fittings in the linear part of the MSD. And decide what is linear or not can be a little bit hard, and this relies too much on the eyes of the person that is looking. For example, if you look here, this MSD, it's hard to say by eye that this is not linear, but this is linear. Of course, looking here, everything seems linear, but in this point here, it's hard to see where the linear regime starts and where the linear regime finishes. One way that we have to evaluate this is the calculation of the beta parameter. What we are doing here is basically we are doing the derivative of the MSD regarding the time. So we are evaluating the inclination of the line regarding the time. And when beta reads a value close to 1, means that we have a linear regime. If you look here to this relation, it's easier to understanding why we are looking for beta equal 1. Because if beta equal 1, that means that everything's linear and the MSD is not going to change regarding the time. Because if we are doing the fitting here, we are looking to the, oh, I forgot the name, sorry. The angular coefficient of the MSD. So if this
slope.
Slope, yes, thank you. if we see this linear, that means that the slope here or the slope here will be the same. So this is why we are looking for a beta that has a value close to 1. However, it's really hard to find a value like specific one. So in general, we can assume that a beta close between 0.9 and 1.2 is good enough. So here, this is what the code is doing. We have the MSD. So we calculate the beta, and the code find a good region, that is this one here, to get the self-diffusion coefficient. And if you look here, there is a small part of the beta that is still inside a good region, but we are not using to the calculation because this is too close to the end of the MSD. And here we know that we have a lot of these spikes here. So let's say that we cannot trust too much in this data. So it's always good to discard the last 10 or 20 or 20% of your MSD. Also, in the last years, I have tried to do that, and a lot of people is doing this in the literature, that is reporting everything regarding your self-diffusion coefficients, because again, this rely too much where you do the fitting. So it's always good when you publish your data, put the beta parameter, the R-squared value for the fitting, try to put the values of the time that you use for your calculation. So in this way, we can communicate everything that we use to calculate the self-diffusion coefficient inside our simulation. You can get self-diffusion coefficients using grommets. So GMX MSD is a really good tool, and it's really fast. And I like a lot this tool because this was the tool that I learned to use with Luciano. And also because in this tool, you can use everything directly from grommets. So you have less opportunity to do mistakes. However, the problem with this GMX MSD, it's because when we calculate, we have these these spikes that we saw in the picture. Another tool that is very good to calculate self-diffusion coefficients is Travis from Kirchner Group. And I think I don't have here, but I like Travis because they have some smooth procedure inside. A second. They have some smooth, no, not this one, smooth procedure inside the code that they can decrease a lot the spikes. So that means that it's easier to find the linear regime. See, it's basically everything here, it's linear. Of the time, it's just a statistical treatment. And this helps me a lot to find the best way, the best region to do. However, the problem when we are using Travis, it's because Travis does not read the files from grommets. So we need to convert the file from grommets to GRO file, PDB file, or XYZ file. And this can lead to some errors. So I really recommend to use Travis to get the self-diffusion coefficient. But if you are doing this, pay attention. So ensure that you are converting your file using the correct way. You are using the correct size of the box, because a lot of mistakes can happen here. But if you know how to do this, go ahead and you can have like this kind of plot here that's easier to find the linear regime. So we have some problems in the diffusion coefficients, because diffusion coefficients, they suffer from size effects. That means that if we compare the data for a part simulation with 200 pairs of any liquid and a data for a simulation with 1,000 pairs, we are going to see difference in the diffusion coefficients, and this is because the size effects. And also, when you compare your simulation data with experimental data, you are comparing data in very different sizes. In one size, you have like Avogadro numbers, and the other size, you have just 100 or some hundreds of pairs. So that means that we need to correct our values to have a better comparison with the experimental data. This is the Yeh and Hammer correction. This is a widely used correction in MED simulations. So using the size of the box and also the viscosity of your material, you can correct your simulation to extrapolate to an infinite size. So if we look here, we have one example. So in black, we have MD simulation data. So here they are changing the size of the box, but when they correct the values, they go here and they go close to the experimental data, that is this blue dashed line here. So how we do this? We use this simple equation here. So P, this is the viscosity of the material, this is the simulation box size, this is the temperature, and this is a constant used determined by the Ewald-like summation. So I don't remember by head the number, but it's basically a constant number that you are always going to use. So if you want to see a very correlation between your self-diffusion coefficient from the MD simulation with the experimental data, you need to do this correction, because if you don't do, you are going to see this kind of a deviation between the experimental and the simulation, and you are going to think that maybe this is the problem of my force field, maybe I use a not good protocol, but it's just a size effect. Also about the size effect, recently, Professor Dietmar from Germany, he published a method in which you can calculate diffusion coefficients without do this correction. So if you use this method, it's a really nice method, worth read. You can obtain self-diffusion coefficients from a rectangular box, and you can have this, your data already with the correction. So it's a really nice method to use. Also here, I said that we need to use viscosity, and sometimes you don't know the viscosity of your system, but you can calculate this by MD simulation, because in general, the viscosity in MD simulation does not suffer from size effects. So you can just do a small simulation box, get the viscosity. Of course, getting viscosity is not a simple task, but you can do this easily by MD simulation to have the Euler correction for your self-diffusion coefficients. Now, let's talk about the ion conductivity. So here we are using also Einstein method. So everything that I said for the self-diffusion coefficient, it's also valid for the ionic conductivity. For example, we do the different time origins. For example, here you can see I change the difference in the time origins. So in black, we are shifting 10 steps. In purple, we are shifting 1,000. Okay, sorry, I thought it was a question. We are shifting 1,000, so we can see here in the MSD the difference. You can see that in black, again, a good definition, but when you look to purple, it's very noisy, and these create a lot of problem to see where we have our linear regime. Also, the problem with the ion conductivity, it's because now we are looking to the movement of different particles together. So this creates this kind of behavior here, because if you compare this with the self-diffusion coefficient, sorry, the MSD for the self-diffusion coefficient, you can see that you have some oscillatory behaviors. So it's hard to see where is your linear regime. For example, maybe we can find a linear regime here, maybe we can find a linear regime here. So it's really hard to say, okay, which part of the MSD I'm going to use. Let me try to show some data here. Okay. So this is the same figure that I show in the paper. So this is the MSD for different contributions. So if you look here, you can see that when we look only to the self terms, those two terms here, they are very sharp. So they are good to find the linear regime, because probably if we do our fitting in any part here, we are going to see very similar results. So 0.1. Yeah, so 044, 041, so very similar parts. But the problem is, when we are looking to the total ion quantity, we are looking to the summation of everything. So the cross terms, these guys here, they are not linear. And because of these terms here, the total ion quantity become this like kind of a oscillatory behavior. So it's really hard to see which part here we should use to get the ion quantity. The best way to, I mean, there's no rule how to do that. In the last years, a lot of people have proposed very different methods to determine the linear regime here. I try to use the beta parameter here. Sometimes work when you have a very good system, a system with a very easy behavior, like you have like a ionic liquid with low viscosity and high temperature. This is okay. But sometimes when you have like very viscous systems, it's hard to find the linear regime here when you use the beta. There's one work from this work here in which they propose to evaluate the linearity of the curve in different places, and based on the data that you have, you can extrapolate what's happened if you have like beta equal 1. This is one approach, but I thought it's a little bit complicated to implement by me. So what I am doing, I'm trying to use different replicas of the same simulation. So if I showed you here, just a second. So here we have in black the average of different MSDs. So you can see that when we have the average, we have a good behavior here. So here we can see the linear regime more easier than when we look to different replicas. And also you can see that very interesting stuff about the MSD for the ion quantity is, since we have the shifting in the times, so we have a better sampling here in small simulation times, and also we are getting the mutual behavior, the mutual displacement of the particles. That means that in small simulation times, we have a good definition. But when we look here, we have a lot of noise. So if you are doing your calculation using the Einstein method, try to look for the behavior in small simulation times, because probably here you are going to find some linear parts that can be just the error of the simulation, not the real behavior of the system. So different than in the MSD for the self-diffusion coefficient. Now you should pay more attention to short simulation times and not long simulation times. And this is intrinsic of the method, so this is not about the material. So it's a recommendation that in major part of the times work. Also, another
pretty good.
that we have here is,
Tuanan, I have a question. Sorry to interrupt.
No.
Those chord curves, those were different simulations of the same system, or was MSD of different particles of the system?
Those are different simulations.
Okay.
I mean, you do your procedure, you equilibrate everything. When you start your production, you can like just copy your box, different directories, change the seed for velocity, and you simulate like 10 times, 5 times.
I see. Okay.
And to be honest, I don't know what is better, because you can also do a different way. You can do like a very long simulation, like 100 nanoseconds, and use like 0 to 30, 30 to 60, 6 to 90. And you can treat this as 3 simulations instead of 1. To be honest, I don't know in which approach you can have a better dynamics, a better description. I think this is maybe more about the resources that you have. Like if you have several nodes, I think it's faster do different calculations. If you have one node that is very fast, maybe you can just use one very long simulation and split the simulation in parts. Okay.
Yeah. Okay. Thanks.
Yeah, and Tuanan, that paper you showed in Alexandre master dissertation, exactly this one.
Sorry.
about that paper before, where you showed the multiple averages.
Okay. Let me remember.
That you said that this paper, this protocol, is a little bit quite expensive,
Okay.
and you didn't get to reproduce well the data.
Yeah, I thought it was a little bit hard for me to implement.
No,
So
yeah. No, this paper, Alexandre and I, we like had a profound reading on this protocol that this guy published. But if you look at the system, that they use it for showing this type of approach, like, is quite different of some correlated systems like ionic liquids, polymers, and so on. That's much more time demanding, to get this type of results.
Yes.
I guess they use it exactly, sodium chloride, something like that, in water.
Yes.
It's a kind of a simple, and a system, and the Newtonian system, it behaves like Newtonian liquid. So, but the thing, I guess, is much more complicated when we are simulating ionic liquids or polymer electrolytes, where the correlation between the ions in the systems is higher than this one, I guess.
Yes. Yes.
And because that, I guess, this approach maybe is valid for these simple, ionic systems, but not too much for complex systems like ionic liquids,
Yeah, this is a very good advice. When you are looking to a procedure to use in your project, try to find what people have done for similar systems than yours. Because as Luciano said, this is totally true. What works in one system sometimes do not work in other systems. For example, so when we get the self-diffusion coefficients, we need to do linear fittings in the MSD, right? Grommux can do this for you. If we do this, GMX, MSD, -8, we have the help here. It's always good to read the helps. And if you read here, you are going to see that Grommux does the fitting to get the self-diffusion coefficients, considering the starting point in 10% of the simulation of the MSD, and the final point in 90%. For systems like, as Luciano said, with weak correlation like water, this is okay. Probably you are going to see a really good result. But if you are working with the ionic liquids, like here, if I start to do my linear, we can do this now. Just a second. For example, if we do what Grommux does, will be something like this. If we do a linear fitting here, probably will not be good. See, it's not linear. So these protocols for Grommux probably work for water, for some low viscosity solvent, but not for ion liquids. So calculating. So I thought for me it was hard to do this. I really like the idea here because I think this can save a lot of time, but for me it was hard to implement in my simulations. This week, I was working closely with Professor Luis Gustavo, and he proposed one way to find the linear regime. We are doing the initial tests. From now, it's working. So I hope in some months everything will be okay and we can share the data, publish the data, because we are working with high correlated systems and we are having very big problems to find the linear part, especially when you have like different people working, so different eyes looking to the MSD is hard to find the same region. But one thing that always work is using different replicas. If you have several simulations, you can improve the behavior. Also, another thing that you can do, as I was telling to Marcel, you can use it one simulation and split this in different simulations. So here we have one simulation. So in orange, this is the total simulation time, and here is like 40 nanoseconds. Here is 30, 20, 10, and 5. If you look here, if we do the log scale, we can see that in small simulation times, they have a very similar behavior. So depending of the material, you can use very short simulations, but depending of the material, you cannot use. So like here, I'm not sure.
I loved so much this way that you showed. Alexandre is here. I guess Jared is too here. I guess, and I was talking to them. I guess last week about the log plot. Okay, I guess this picture that you showed now was amazing because highlighted the power of the log plot. Okay, exactly, to capture the linear regime. Okay, if Alexandre and Jared, okay, can comment this, it's amazing. You know, guys, this is the way that the log plot can help us. Okay, for this type of calculations, for example. Okay, remember, Alexandre and Jared. Nice, Tuanan. Thank you. Good.
Yeah, if you use the log, it's way easier to see where is the linear part. But remember,
yeah, because the log is exactly, okay, helping us to scale up, okay, or fit the scales, different scales in the same region, okay, that it's pretty easy to see exactly the behavior for different, okay, lines or curves.
So always use the log scale to try to see, and to be honest about splitting your trajectory in different parts using different replicas, I don't know yet what is better. You should consider your material, your resources, your time. There's a nice paper about it to read that is more similar to what we do. That this is the paper from, just a second. Yeah, this paper from Jindal. So he does a lot of tests about how to get the ionic conductivity. But again, he gives some recommendations about the ionic liquid that he's using that can be useful for some ionic liquids, but for not the others. But it's a really nice paper to read to understanding the problem in the collective MSD, because here they show a lot of different simulation times, different sampling times. So it's a really nice paper and worth a lot to read to understand.
Verma, yeah. Could you show the title of the paper?
Yeah.
Yeah, nice, good. Yeah, recent paper. I don't know if I saw this paper. I don't know, but nice, good. Okay, Jidon Shah. Yeah, I believe, Alexandre, we included, okay, this paper in our work, okay?
Listen, I just need to do some advice for the Tuanan people. Guys, you have a meeting, so please go to the meeting. Don't skip the meeting, okay?
Okay.
In our paper, we were able to get the beta for the MSD collective, but I tried for other more complicated. In this paper here, we use some kind of beta. Hard, depending of the sampling, depending of the system, so it's not too easy.
Yeah, pretty good.
So best way to do what you did. Put everything like in the support information. Oh, I did this.
Okay, thanks, Tuanan. Thanks, Luciano. And thanks, Tuan. We will see you later. Thank you. I have a meeting.
Let me show more data here. Just a second. About the averages. So this is the same simulation, literally the same simulation. I just use a small number in the average in the code, so you can see that when we increase the number of average, so here is just 5 simulations, you can improve a lot the behavior of the MSD. But again, no rule about the number of simulations, the size of the simulation, so you need to test. It's basically this. Okay, so to finish about the first field that you are going to use in your work, keep in mind that this is one thing that I have learned a lot in the last years. All the first fields are models. First fields have good sides and bad sides. Each one does not matter how fancy or how expensive is the first field. So the best way is always trying to balance the cost of the project, what you want to do, and what the first field can do. For example, we know that the polarizable first fields using DRUD models, they can be more, they can predict the transport properties more close to experimental data. So the values that we are going to have will be closer to the experimental data than in the non-polarizable first field. However, those first fields are very expensive, way more expensive than the usual one. So if you use a more expensive first field, you need to decrease the simulation time, you need to decrease the amount of replicas. If you use a more cheap first field, maybe you can have more replicas, you can have a better statistics. So it's a balance between what I want to do, what I can do, and what I need to do. For example, I have keep in my mind in the last years that when I'm doing MD simulations, I'm looking for trends. I'm trying to explain physical behavior, so the value that I'm getting maybe is not too important. What is important is the trend that I can see. For example, here, we compare polarizable first fields with non-polarizable first fields, with scaled charge first fields, and with the engulf first field, that is a non-scalable charge in which the Lennard-Jones terms were empirical changed to match experimental data. And when we look here, in this gray area here, that is the experimental data, we see that the polarizable, the engulf, and also the scaled charges, all of them can match the experimental data. The difference is how far or how close I am from the experimental data. So based on this data here, I cannot say if you should use a polarizable, non-polarizable, scaled charge, not scaled charge. Looking here, all the data is very similar. But when you look here to the not scaled charge, not polarizable first field, you can see a big difference in the data regarding the experimental data. So from looking here, we can say, okay, if I do not use polarizable or adapted Lennard-Jones or scaled charge, I will be far away from the experimental data. However, when we look here, this is we are dividing the diffusion of the cation by the diffusion of the anion. So here we can try to see a trend inside our data, and looking to the trend, we have the same trend for everybody. So again, gray area is the experimental data. All the first fields go to the experimental data. So looking here to this data here, we see, okay, those first fields have a better description of the value, but all the first fields have a really good description of the physical behavior of the material. So in the end of the day, you need to think what you want to describe. If you want to describe trends, okay, all the first fields can have a good trend. If you want to describe a really good value, okay, you need to go to more specific first fields. But as we were talking, we suffer from sampling in the conductivity. So maybe having a balance between a large number of simulations and a cheaper first field can be better to describe the system than using a more expensive first field and a small number of short simulation times. The same happens here when we look to the ionic conductivity. When we look here, we see again, those 4 first fields are close to experimental data, non-polarizable far away. But when we look to the transport numbers in which we can see trends, everything is quite similar. So in my postdoc research, I have worked a lot with different different methods to try to see how to improve the charge pressure. Just try to keep in mind what you can. This is just a personal advice for. And here is some recommended researcher. I will send all of those papers to Luciano so he can share with you guys. I try to create a small library with some papers from best practices, different methods to calculate the properties. And also, I don't know if you guys know this, but for MD people, this magazine here is a really nice magazine to read, this live con best practices, because they publish a lot of tutorials, best practices, and they are always updating, and they also provide you some inputs to reproduce the data. So it's a really nice paper to read to understand how to do this stuff. So this is what
very good.
I had to show. So thank you. And of course, if you have questions, I'm here. Also, if you have questions, but not now, you can just write to me, no problem.